Hello everyone, my name is Azak and I will be walking you through this Jupyter notebook written in Python. This notebook is focused on building a machine learning model to make predictions on a given dataset. The first cell in this notebook is a markdown cell that outlines the pipeline of this project. It starts with importing necessary packages, importing data, checking the data, partitioning the data into target and features, extracting numerical and categorical feature names, defining a validation strategy, preprocessing the data, building the model, making predictions, and finally exporting the submission file. Additionally, the cell also poses critical thinking questions that we should ask ourselves throughout the project, such as why we are doing certain things, what we are trying to achieve, when we should perform certain tasks, how we should approach certain problems, and where we can find resources to help us. Moving on to the first code cell, it starts with importing necessary packages. This is a common practice in any Python project as it allows us to use functions and methods from these packages throughout our code. Some of the packages being imported in this cell include pandas, NumPy, matplotlib, cborn, and scikit-learn. I will now move on to the next cell and explain it step by step. In this cell, we are importing necessary packages for our project. The first package being imported is pandas, which is a popular data manipulation library in Python. We will be using pandas to read in our data and perform various operations on it. Next, we are importing train_test_split from scikit-learn's model_selection module. This function will allow us to split our data into training and testing sets, which is a crucial step in building a machine learning model. We are also importing standard scalar from scikit-learn's preprocessing module. This function will help us standardize our numerical features so that they have a mean of 0 and a standard deviation of 1. This is important because it can help improve the performance of our model. Next, we are importing logistic regression from scikit-learn's linear_model module. This is the algorithm we will be using to build our model. We are also importing classification_report from scikit-learn's metrics module. This function will allow us to generate a report that shows various metrics for our model's performance, such as precision, recall, and F1 score. Finally, we are importing matplotlib.pyplot as PLT. This package will allow us to create various visualizations throughout our project. That's it for this cell. In the next cell, we will start importing our data. In the next cell, we will be importing our data. In this cell, we are importing our data. First, we are using pandas read_CSV function to read in our training data from a CSV file located at input/train.csv. We are storing this data in a variable called train. Next, we are using the same function to read in our test data from a CSV file located at input/test.csv. We are storing this data in a variable called test. Finally, we are using the same function to read in a sample submission file from a CSV file located at input/sample_submission.csv. We are storing this data in a variable called submission. That's it for this cell. In the next cell, we will start exploring our data. Checking data is an important step in the data analysis process. It helps us understand the structure and content of our data, identify potential issues, and make informed decisions about preprocessing, cleaning, and analysis. In this cell, we will be checking our data for the following reasons. Data quality, ensuring data is accurate, consistent, and reliable. Data exploration, understanding the distribution of features and target variables. Missing values, identifying missing or null values that might need to be handled. Outliers, detecting unusual or erroneous data points that could impact analysis. Data types, verifying if columns have appropriate data types. Feature engineering, offering insights for creating new features or transformations. We will be using various pandas functions to achieve this. Let's get started. In this cell, we are using the info function from pandas to display basic information about our data frame. This includes the number of entries, the data types of each column, and the memory usage. We can see that our data frame has 18,359 entries and 14 columns. We also see that some columns have missing values, such as the gender column, which has 4,098 missing values. This information gives us a general idea of the structure and content of our data. However, we need to dig deeper to identify any potential issues. In this cell, we are using the describe function from pandas to display summary statistics of our numeric columns. This includes the count, mean, standard deviation, minimum, maximum, and quartile values. We can see that our training_hours column has a wide range of values, with a minimum of 1 hour and a maximum of 336 hours. The city_development_index column has a mean of 0.847, indicating that most of the cities in our dataset are highly developed. These statistics can give us insights into the distribution and range of our data, which can help us make decisions about how to preprocess and analyze it. In this cell, we are using the head function from pandas to display the first few rows of our trained data frame. This can give us a quick overview of the structure and content of our data. We can see that our data frame has several columns, including enrollee_in, city, gender, relevant_experience, enrolled_university, education_level, major_discipline, experience, company_size, company_type, training_hours, and target. The target column indicates whether a given enrollee has been hired or not, with a value of 1 indicating that they have been hired and a value of 0 indicating that they have not. We can also see that some of our columns have missing values, indicated by nan. We will need to handle these missing values appropriately during our data preprocessing step. In this cell, we are checking for missing values in our trained data frame using the isNull function from pandas. This function returns a data frame of the same shape as our original data frame, with true values indicating missing values and false values indicating non-missing values. We then use the sum function to count the number of missing values in each column. We can see that several columns have missing values, including gender, enrolled_university, education_level, major_discipline, experience, company_size, and company_type. We will need to handle these missing values appropriately during our data preprocessing step. In this cell, we are checking for unique values in the categorical columns of our trained data frame. We use the select_dtypes function from pandas to select only the columns with object data type, which are typically categorical columns. We then loop through each selected column and use the unique function to display all the unique values in that column. We can see that some columns have a large number of unique values, such as city, while others have a smaller number of unique values, such as enrolled_university. We will need to handle these categorical variables appropriately during our data preprocessing step, such as by using one-hot encoding or label encoding. In this cell, we are creating a box plot to check for outliers in the numeric columns of our trained data frame. We use the plot function from pandas and specify the kind parameter as box to create a box plot. We also set the vert parameter to false to display the box plot horizontally and specify the figsize parameter to set the size of the plot. We then add a title to the plot using the title function from matplotlib and display the plot using the show function. Box plots are a useful way to visualize the distribution of data and identify any outliers. Outliers are data points that are significantly different from the majority of the data and can have a significant impact on our analysis. We will need to handle any outliers appropriately during our data preprocessing step. In this markdown cell, we are indicating that we will be checking the target variable in the next code cell. The target variable is the variable we are trying to predict in our machine learning model, which in this case is the target column in our trained data frame. Checking the target variable is an important step in our data analysis as it allows us to understand the distribution of the target variable and identify any potential issues, such as class imbalance. In this cell, we are checking for class imbalance in the target column of our trained data frame. We first use the value_counts function to count the number of occurrences of each class in the target column. We then calculate the percentage of each class in the target column by dividing the class counts by the total number of rows in the trained data frame and multiplying by 100. Class imbalance occurs when one class in the target variable is significantly more prevalent than the other classes. This can lead to biased machine learning models that perform poorly on the minority class. We will need to handle any class imbalance appropriately during our data preprocessing step. In this cell, we are simply printing out the class counts of the target column that we calculated in the previous cell. We use the print function to display the class counts in a readable format. As we can see from the output, there are 15,934 instances of the 0 class and 2,425 instances of the 1 class in the target column. This indicates that there is some class imbalance present in our dataset, as the 0 class is significantly more prevalent than the 1 class. We will need to handle this imbalance appropriately during our data preprocessing step. In this cell, we are printing out the percentage of each class in the target column that we calculated in the previous cell. We use the print function to display the percentages in a readable format. As we can see from the output, the 0 class makes up 86.79% of the target column, while the 1 class makes up only 13.21%. This confirms that there is indeed class imbalance present in our dataset. We will need to handle this imbalance appropriately during our data preprocessing step to ensure that our machine learning model is not biased towards the majority class. In this markdown cell, we have a section header titled Partition Data followed by 2 bullet points. The first bullet point mentions splitting the data into Y and X for both the training and testing sets. The second bullet point mentions using the train-test-split function to split the data into training and testing sets. We will see the implementation of this in the next code cell. In this cell, we are partitioning our data into Y and X for both the training and testing sets. We first create the Y variable by selecting the target column from the trained data frame. We then create the X variable by dropping the enrollee_id in target columns from the trained data frame using the drop function. Next, we create the X_test variable by dropping the enrollee_id column from the test data frame using the drop function. We exclude the enrollee_id column from both X and X_test because it is not a useful feature for our machine learning model. By separating our data into Y and X variables, we can easily feed our data into machine learning models for training and testing. In this cell, we are using the train_test_split function again to split our X and Y variables into training and validation sets. The test_size parameter is set to 0.2, which means that 20% of the data will be used for validation. The random_state parameter is set to 42 for reproducibility. By splitting our data into training and validation sets, we can evaluate the performance of our machine learning model on data that it has not seen before. This helps us to avoid overfitting and ensures that our model is generalizing well to new data. In this cell, we are printing the shapes of our resulting datasets using the shape attribute. We can see that our training set X_train has 14,687 rows and 12 columns, while our validation set X_val has 3,672 rows and 12 columns. Our Y_train and Y_val variables have 14,687 and 3,672 rows respectively, as they only contain the target variable. We also see that there is an X_test variable, which suggests that we have a separate test set that we have not split yet. We will likely split this test set later on to evaluate the final performance of our model. In this markdown cell, we are likely going to extract the names of the numerical and categorical features in our dataset. This is an important step in data preprocessing as it allows us to apply different transformations to different types of features. For example, we may want to scale our numerical features to have zero mean and unit variance, while leaving our categorical features as one-hot encoded variables. Let's move on to the next code cell to see how we extract these feature names. In this code cell, we are separating the names of the numerical and categorical columns in our training set x_train. We use the select_dtypes method to select columns based on their data types. We pass in the argument include equals int64, float64 to select all columns with numerical data types. We then use the columns attribute to extract the names of these columns and store them in the numerical_columns variable. Similarly, we pass in the argument include equals object to select all columns with categorical data types. We again use the columns attribute to extract the names of these columns and store them in the categorical_columns variable. By separating the numerical and categorical columns, we can apply different preprocessing steps to each type of feature. For example, we may want to scale our numerical features and one-hot encode our categorical features. In this code cell, we simply print out the lists of numerical and categorical column names that we extracted in the previous cell. This is just a sanity check to make sure that we have correctly identified the types of features in our dataset. As we can see from the output, we have two numerical columns, city_development_index and training_hours, and 9 categorical columns, city, gender, relevant_experience, enrolled_university, education_level, major_discipline, experience, company_size, and company_type. Now that we have identified the types of features in our dataset, we can move on to preprocessing them in the next steps. In this markdown cell, we are introducing the concept of preprocessing and specifically, the preprocessing steps we will be taking in this notebook. Preprocessing refers to the steps taken to prepare the data for machine learning algorithms. This can include tasks such as cleaning the data, handling missing values, scaling the features, and encoding categorical variables. In this notebook, we will be performing the following preprocessing steps. 1. Handling missing values. 2. Encoding categorical variables using one-hot encoding. 3. Scaling numerical features using standardization. We will be implementing these steps in the upcoming code cells. In this code cell, we are performing the first preprocessing step, which is handling missing values in the numerical columns. We start by importing the simple imputer class from the sklearn.impute module. This class provides a simple way to impute missing values in a dataset. Next, we create an instance of the simple imputer class and specify the strategy we want to use for imputing missing values. In this case, we are using the median strategy, which replaces missing values with the median value of the column. We then fit the imputer instance on the numerical columns of the training set using the fit method. This calculates the median value for each column and stores it in the imputer instance. Finally, we use the transform method to impute missing values in the numerical columns of the training, validation, and test sets. We overwrite the original columns with the imputed values. By performing this step, we ensure that there are no missing values in the numerical columns, which is necessary for many machine learning algorithms to work properly. In this code cell, we are performing the second preprocessing step, which is handling missing values in the categorical columns. We start by importing the simple imputer class from the sklearn.impute module, just like in the previous code cell. Next, we create an instance of the simple imputer class and specify the strategy we want to use for imputing missing values. In this case, we are using the constant strategy, which replaces missing values with the constant value that we specify. We set the constant value to missing. We then fit the imputer instance on the categorical columns of the training set using the fit method. This calculates the constant value for each column and stores it in the imputer instance. Finally, we use the transform method to impute missing values in the categorical columns of the training, validation, and test sets. We overwrite the original columns with the imputed values. By performing this step, we ensure that there are no missing values in the categorical columns, which is necessary for many machine learning algorithms to work properly. In this code cell, we are performing the third preprocessing step, which is scaling the numerical columns. We start by importing the standard scalar class from the sklearn.preprocessing module. Next, we create an instance of the standard scalar class. We then fit the scalar instance on the numerical columns of the training set using the fit method. This calculates the mean and standard deviation for each column and stores it in the scalar instance. Finally, we use the transform method to scale the numerical columns of the training, validation, and test sets. We overwrite the original columns with the scaled values. By performing this step, we ensure that the numerical columns have the same scale, which is necessary for many machine learning algorithms to work properly. In this code cell, we are performing the fourth preprocessing step, which is encoding the categorical columns. We start by importing the ordinal encoder class from the sklearn.preprocessing module. Next, we create an instance of the ordinal encoder class. We then fit the encoder instance on the categorical columns of the training set using the fit method. This creates a mapping between the unique values in each column and an integer value. Finally, we use the transform method to encode the categorical columns of the training, validation, and test sets. We overwrite the original columns with the encoded values. By performing this step, we ensure that the categorical columns are represented numerically, which is necessary for many machine learning algorithms to work properly. In this Markdown cell, we are introducing the next section of the Jupyter Notebook, which is the model section. In the model section, we will be building and training a machine learning model to predict the target variable based on the preprocessed data. We will start by importing the necessary libraries and classes, defining the model architecture, compiling the model, and then fitting the model on the training data. We will then evaluate the performance of the model on the validation data and make any necessary adjustments before testing the final model on the test data. Overall, the goal of the model section is to create a machine learning model that can accurately predict the target variable based on the input features. In this code cell, we are creating an instance of the logistic regression class from the sklearn.linear_model module. We set the max_iter parameter to 1000 and the solver parameter to LBFGS. These are hyperparameters that control the behavior of the logistic regression algorithm. Next, we fit the logistic regression model on the preprocessed training data, x_train and y_train, using the fit method. This trains the model on the training data and allows it to learn the relationship between the input features and the target variable. Once the model is trained, we can use it to make predictions on new data. We will evaluate the performance of the model on the validation and test data in the next section of the Jupyter Notebook. In this Markdown cell, we are introducing the next section of the Jupyter Notebook, which is the predict section. In the predict section, we will be using the trained machine learning model to make predictions on new data. We will start by loading the test data, pre-processing it using the same steps as the training and validation data, and then using the trained model to make predictions on the pre-processed test data. We will then evaluate the performance of the model on the test data and make any necessary adjustments before deploying the final model in a production environment. Overall, the goal of the Predict section is to use the trained machine learning model to make accurate predictions on new data and ensure that the model is performing well before deploying it in a real-world application. In this code cell, we are using the trained logistic regression model to make predictions on the preprocessed training, validation, and test data. We use the predict method of the logistic regression class to make predictions on each of the datasets, x_train, x_val, and x_test. The predicted values are stored in the variables y_train_pred, y_val_pred, and y_test_pred, respectively. We will use these predicted values to evaluate the performance of the model on each of the datasets in the next section of the Jupyter Notebook. By comparing the predicted values to the actual target values, y_train, y_val, and y_test, we can assess how well the model is able to generalize to new data and make accurate predictions. This is an important step in the machine learning workflow, as it allows us to identify any issues with the model and make improvements before deploying it in a real-world application. In this Markdown cell, we are introducing the next section of the Jupyter Notebook, which is the Check Accuracy section. In this section, we will be evaluating the performance of the trained machine learning model on the preprocessed training, validation, and test data. We will start by calculating the accuracy of the model on each of the datasets, x_train, x_val, and x_test, using the accuracy_score function from the sklearn.metrics module. We will then compare the accuracy scores to determine how well the model is able to generalize to new data and make accurate predictions. Overall, the goal of the Check Accuracy section is to ensure that the trained machine learning model is performing well on the preprocessed data before deploying it in a real-world application. In this code cell, we are creating classification reports for the trained logistic regression model on the preprocessed training and validation data. We use the classification_report function from the sklearn.metrics module to generate the reports. The classification_report function provides a detailed summary of the precision, recall, F1 score, and support for each class in the classification problem. We create two classification reports, one for the training data and one for the validation data, and assign them to the variables train_classification_report and val_classification_report, respectively. These reports can be used to evaluate the performance of the model on each class and identify any areas where the model may be struggling. It is important to note that we may encounter a warning message when running this code cell, which is related to the undefined metric warning in the sklearn.metrics module. This warning message can be ignored for now, but we may need to address it in future iterations of the code. Overall, the goal of this code cell is to generate classification reports for the trained machine learning model on the preprocessed data and evaluate its performance on each class in the classification problem. In this code cell, we are printing the classification report for the training data. We use the print function to display the report on the console. The train_classification_report variable, which we created in the previous code cell, contains the classification report for the training data. The report provides a detailed summary of the precision, recall, F1 score, and support for each class in the classification problem. In this specific example, we can see that the model has a high precision and recall for class 0, but a very low precision and recall for class 1. This information can be used to identify areas where the model may be struggling and make improvements to the model in future iterations. Overall, the goal of this code cell is to display the classification report for the training data and provide insights into the performance of the model on each class in the classification problem. In this code cell, we are printing the classification report for the validation data. We use the print function to display the report on the console. The val_classification_report variable, which we created in the previous code cell, contains the classification report for the validation data. The report provides a detailed summary of the precision, recall, F1 score, and support for each class in the classification problem. In this specific example, we can see that the model has a high precision and recall for class 0, but a very low precision and recall for class 1. This information can be used to identify areas where the model may be struggling and make improvements to the model in future iterations. Overall, the goal of this code cell is to display the classification report for the validation data and provide insights into the performance of the model on each class in the classification problem. In this markdown cell, the author is indicating that they will now make a submission and export the results. This likely means that they have trained a model on a dataset and are now ready to use that model to make predictions on a new set of data. Once the predictions have been made, the author will likely export the results in a specific format, such as a CSV file, so that they can be submitted to a competition or shared with others. The next code cell will likely contain the code to make the predictions and export the results. In this code cell, we are creating a pandas data frame called submission. The data frame has two columns, enrollee_id and target. The enrollee_id column contains the enrollee_id values from the test data frame, which is the dataset that we want to make predictions on. The target column contains the predicted values for the test dataset. The predicted values are stored in the y_test_pred variable, which we created in a previous code cell. By creating this data frame, we can easily export the predicted values in a specific format, such as a CSV file, for submission or sharing with others. Overall, the goal of this code cell is to create a data frame containing the predicted values for the test dataset and prepare it for export. In this code cell, we are defining the output file path for our submission. The output_path variable is set to output/submission.csv, which means that our submission will be saved in a folder called output and the file name will be submission.csv. After defining the output file path, we use the to_csv method to export the submission data frame to a CSV file. The index equals false parameter ensures that the index column is not included in the exported file. Finally, we print a message indicating that the submission data frame has been exported to the specified output path. Overall, the goal of this code cell is to export the submission data frame to a CSV file so that it can be submitted or shared with others. In this code cell, we are using the head method to display the first few rows of the submission data frame. The output shows the enrollee_id values from the test dataset and the corresponding predicted values for each enrollee_id. This is a quick way to check that the data frame has been created correctly and that the predicted values are in the expected format. Overall, the goal of this code cell is to display the first few rows of the submission data frame for verification purposes. This is an empty code cell, which means that there is no code to execute and no output to display. It's common to have empty code cells in Jupyter notebooks, either as placeholders for future code or as a way to separate different sections of the notebook. In this case, we can use this empty code cell to add any additional code or explanations that we want to include in the notebook. Overall, the goal of this code cell is to provide a blank space for additional content in the notebook. That concludes our tutorial on the HR Analytics Job Change of Data Scientists dataset. We started by exploring the data and performing some basic data cleaning and preprocessing. Then, we used various machine learning algorithms to train models and make predictions on the test dataset. We evaluated the performance of our models using various metrics and selected the best model for submission. Finally, we created a submission file in the required format and displayed the first few rows of the submission data frame for verification purposes. I hope this tutorial was helpful in understanding the process of working with a real-world dataset and building machine learning models. Thank you for watching.